Welcome to Chem We Talk, a channel where we're not afraid to talk about any chemistry topic. In today's video, we'll go over a challenging problem involving the pH calculation of a salt that was derived from a polyprotic acid. Before continuing watching this one, make sure you check the other videos in the channel that go over the pH of solutions containing salts. I believe it's going to be very helpful to follow this one. Okay, the links to those videos can all be found in the description right below. Alright, no further ado, let's move on to the actual problem that we're going to discuss today, which is calculating the pH of a 1 molar solution of lithium bisulfate. As usual, whenever we have a salt, we break that salt apart into its ions. In this case, they're going to be lithium plus and HSO4 minus, and we see which base and which acid produce those ions. So in the case of lithium plus, we have LiOH, which is a strong base, and we know that strong bases, when you put those in water, they break apart completely in a single error reaction, which means that once it breaks apart, it does not go backwards. Therefore, lithium plus is considered a spectator ion. H2SO4 is the acid that generated a HSO4 minus ion present in your salt, and that is also a strong species. In this case, it's a strong acid. And once that reacts with water, it also proceeds in a single error reaction, producing H3O plus and HSO4 minus. And in principle, you would think, okay, yeah, the reaction does not go backwards, therefore HSO4 minus would be spectator ion, and that salt would be neutral. But the question now, is it really? So the fact that this problem is challenging probably tells that something different is going to happen. Okay, so before we actually go into H2SO4 and HSO4 minus, let's start with the strong HCl case. Okay, HCl, as a strong acid, reacts with water. It donates its hydrogen, producing H3O plus and Cl minus in a single error reaction, as discussed, which means that this reaction does not go backwards. It only goes from left to right as expected, which means that once we have the Cl minus trying to react back and behaving as a base, in this case would accept the hydrogen from water, producing OH minus HCl, this reaction does not occur because HCl will not stay as HCl as a whole molecule, because as a strong species, it wants to break apart completely. So if this reaction would happen, it would go this way very, very quickly and goes right back to this one. So this reaction does not happen. Okay. So in this case, because this reaction does not happen, the Cl minus does not have the ability to produce any H plus or OH minus, which in this case, and it's called a spectator ion. Okay, let's see what's the difference between the HCl case and H2SO4. At first, let's just react with water again. H2SO4 has a hydrogen. It can donate its hydrogen to H2O, producing H3O plus and HSO4 minus. And as normal, the reaction, as expected for a strong acid, would go from left to right, and it does not like to go backwards. Okay, so it happens in one direction, which means that if you would bring that discussion about Ks, remember Ks is just products over reactants. And if you're removing the first hydrogen of HSO4 minus, this is a strong acid, goes all the way to the right. So your products would be infinitely compared to your reactants. That's why we call the Ka for a strong acid usually infinity. Okay, so if by any chance we try to have the HSO4 minus, which was a product there, reacting with water, and in this case HSO4 minus would behave as a base, accepting the hydrogen back to reform H2SO4 and producing OH minus, this reaction would not occur, which means that HSO4 minus is still a spectator ion as a base. So far, it is behaving exactly like HCl. But the difference is, what happens with HSO4 minus if it doesn't behave as a base? Remember, HSO4 minus has another hydrogen here that can also be donated or lost, okay? Which means it can also behave as an acid. So if it donates its hydrogen to H2O, it would produce H3O plus and SO4 2 minus. And remember our list of strong acids, HSO4 minus not on it, which means this here would be a weak acid. And it turns out we have the Ka value, and you see here it's called Ka2, and that is in respect to H2SO4. So the first Ka, which we had here, Ka1, was the removal of the first hydrogen. The removal of the second hydrogen would be the Ka2, which is in fact like a very high number. If you can remember, for example, acetic acid, we have 1.8 times the -5, so -2 is still a very strong acid. It is a strong weak acid. Okay. So yeah, so the difference is H2SO4 minus is going to be a weak acid. All right. So going back to our initial chart here, we can see now that Li plus, in fact, is going to be a spectator ion, but HSO4 minus, although it is a spectator conjugate base, it is a weak acid as well. So the salt will be acidic, and we'd expect the pH to be lower than 7. All right, so now that we saw that lithium is a spectator ion, we can rephrase this problem by saying calculate the pH of solution that is only made of HSO4 minus. And we just saw that HSO4 minus is a weak acid. So that begs the question, how do we calculate pH of weak acids? Again, there's another video on the channel that goes in more detail, but in summary, every time you have a weak acid, you just react with water and set up a nice table. Okay, so in our case, we have HSO4 minus in water. This one's behave as an acid, right? So it's going to donate its hydrogen to H2O, producing H3O plus and SO4 minus, and we set up our ice table. Remember, liquids do not interfere with the equilibrium constant, so or your equilibrium expression, so they just put a dashed line here. For your initial concentration, the problem said it was 1.0, and no information was provided about your product, so we can assume those are 0. For the zero, remember, if it is a reactant, we're going to put a negative sign, and if it is a product, we're going to put a positive sign, and then we're going to put x's matching the coefficients. So all the coefficients are 1s, right? So 1 HSO4, 1 H2O, so it's going to be minus x, and plus x, and then the E row, you just read the first two all together. It's going to be 1 minus x, and x. Once you do your products of reactants, you're going to get x times x divided by 1 minus x. That's going to be equals to your basically x squared over 1 minus x. And that is going to be equal to your K2 that we just saw was 1.2 times 10 to the negative 2. Okay, so first thing you're going to do, I'm going to keep making the assumption that this x is going to be so small that we don't need to care about it. So I'm just going to get x squared equals to, if I multiply everything here by 1, it's going to be 1.2 times the negative 2 times 1. That is the same number, x squared equals 1.2 minus 1.2 times 10 to the negative 2. When you take the square root of it, you get x equals 1.09 times 10 to the negative 1. And you know, if you go back to your table, x means, in this case, the concentration of H3O plus at equilibrium. So if you want to calculate the pH, you simply take the negative log of that number, and you get 0.96, which is a very, very low number, which kind of corroborates the fact that HSO4 minus is a strong weak acid. But just let's check one last thing. Remember, when the cases where we can assume that x is negligible is only when we have your x divided by your initial concentration times 100 is less than 5%, which means that your percent ionization is less than 5%. Let's just double check one thing here. So our x was 1.09 times the negative 1. Our initial concentration was 1. And once we multiply that by 100, we get 10.9%. So it turns out that, fortunately, we need to use a quadratic equation, and it's going to take up a little longer to do it. Okay, so if you don't remember, here's the quadratic, how you solve the quadratic equation. But for that, we need to get an equation that looks like this one, some ax squared plus bx plus c. So what we're going to do now is we're going to multiply this k by 1 and then minus x by the k. Okay, so we're going to get x squared equals to 1.2 times the negative 2, which was a product between 1 and this number, minus x times this, which is going to be minus 1.2 times the negative 2x. But for the quadratic equation, we need to move everything to one side and set it up equals to 0. So I'm going to rearrange this equation, and I'm going to get x squared plus this one. Remember, this minus 1.2 times the negative x was with a negative sign on this side. If I move to the other side, that becomes positive. Minus 1.2 times the negative 2. This one was positive on the right side, so if I move to the left side, it's going to become negative, and we have this. And remember, so we need to find our A, B, and C. So our A will be just 1. Our B's and C's in this case are going to be exactly the same, 1.2 times the negative 2. Once I plug it in, all those numbers in the equation, you're going to get two answers, one that is positive, one that is negative. And let's just look at our stable. Would it make sense to have an x being 0.104? Sure, yeah, this number is smaller than your initial concentration. That's like a positive number, that everything is fine. If I were to plug this negative number, it doesn't make any physical sense to get a negative concentration, right? Negative concentration does not exist, so we just ignore this answer and stick with this one. And again, the x is going to be equals to your H3O plus concentration at equilibrium. When you take the negative log of it, you get 0.98. So one thing we need to highlight here, we got 0.98 when we use the quadratic and 0.96 when we ignore the x and did not do it. And you're going to say, oh, those numbers are very, very similar, so we don't need to worry about it. But yes, we do need to worry, especially when the concentrations are smaller for initial acid. Okay, so in this case, we have a 1 molar solution, which is very highly concentrated. More real life example, let's say you have a 0.1 molar solution. I did the calculations here, and if you had ignored x, you would get 1.46. If you didn't, it would be 1.53. So the difference keeps getting worse and worse. For a ballpark estimation, it's okay to neglect it, but for a real exam or a homework, I would recommend doing the quadratic. Okay, so in summary, please be careful when dealing with salts derived from polyprotic acids. So the anion of a salt that's derived from polyprotic acid will behave as spectator only as a base. However, it will also behave as a weak acid, so we need to be careful. And also just pay attention to the fact that most, especially for the LiHSO4 case, because it is like a very strong weak acid, we will need to use a quadratic equation to solve for x in the ice table, especially when the concentrations are lower. When you're dealing with other polyprotic acids, you might be luckier and have like a lower Ka, but always make sure you check your assumptions. All right. So thank you again for watching the video. Make sure you subscribe to the channel, follow us on Instagram, and please leave any comments with suggestions, comments, and other problems you want us to solve. Thank you.